All right.
It's really like
How you guys doing today?
Excited classes.
All right. Today we're going to look at the latest set of problems. Today we're going to go over the homework that you look very nice today.
Thank you.
Today we're going to go over the homework, and then we're going to go through convective stability. We're going to go two different ways through how a star is stable, or a pot of water on the stove. The first thing we're going to do works for a pot of water or a star. It's kind of nice. It's pretty simple physics. That's one of the great things about fluid dynamics is it's accurate on a whole wide range of scales. It describes a continuous fluid or a continuous stuff, regardless of where you how big it is. So, okay, let's just jump right to it. So, starting with the continuity equation, find an expression for the full derivative d rho dt. Did anybody have any? I flipped through the homeworks, but haven't graded them yet. Seemed like everybody did this one just fine. So you start with continuity, which is partial rho partial t, partial rho v partial x. Expand this out with product rule, and then recognize that this plus this is the full derivative. No, this plus this is the full derivative. The v dot grad, this is v times the derivative acting on rho. That's the convective part of the total derivative. So these two things are the total derivative. And you're just left with the time derivative of rho is minus rho div v. And this is kind of a simple thing to do, but it's an important result that div v and the time derivative of rho are so tightly related to each other. So if you want something to get denser, you have to have a big negative divergence. Full stop. There's nothing else weird about that. So this is one of the things that underpins a lot of models of star formation. So when we model star formation, a lot of times we just look for, say I have a big fate galaxy and I want to turn some bits of it into stars, what I look for are places where div v gets large and negative, because that's where I know that the time derivative of the density is getting large, so I can put a star there. Okay, so the second problem, where's my controller? Here we are. So if you blow over the top of a bottle, by how much does the pressure inside the bottle drop relative to the ambient pressure? Use Bernoulli's equation and make stuff up. So this homework is full of go find some numbers and make it up. That's not the last time that's going to show up in these homeworks, because pulling numbers out of the air and then doing stuff with them is really what you do as a physicist. So as a physicist, your job is really to come up with some number that explains something based on other numbers that you know. So we start off with 1/2 rho v squared plus p plus gh equals a constant. Now h is not changing appreciably when I'm blowing over the top of a bottle. If it were later in class, this would be more dramatic, but this is going to give a high squeaky noise. That wasn't too bad. The height from one side of my flow to the other side of the flow is not large compared to gravity. I'm basically blowing this way, basically blowing flat. I can blow at about 10 meters a second. So I got that by estimating the volume of my lungs, filling up my lungs all the way, and exhaling and counting how long it takes. Say I've got a 1 centimeter hole in my mouth, and I just timed that. And I got about 10 meters a second. So would you guys get substantially different numbers for that? I think that's about what people got, was on the order of 10, 15 meters a second. The density of air is 1.2 kilograms per cubic meter. Ambient pressure is 100 kilopascals. And the air in my stream is moving with a velocity v and has a pressure p. The air in the bottle has a pressure p and no velocity. So this one has to be equal to ambient pressure. So this is the atmospheric pressure, 100 kilopascals. Why? Because I know that it's that before I start blowing on it. And when I start blowing on it, I'm not doing anything immediately anyway. I'm not doing anything. So the lower pressure is just 1 kilopascal. And this is the pressure in your air that's just been reduced by however hard you're blowing. So you go through
So basically, you just drop in this and this into here and take the difference, and you get that the difference should be about
80 or 100 pascals. So we're at like 1 part in 10 to the 4 of, or 1 part in 10 to the 5. So if it's 100 pascals and the atmosphere is 100 kilopascals, then we're off by 1 part in 1,000. That's right. So a small pressure perturbation, but one that easily can make even though it's small, it makes a noticeable effect, right? This is a small perturbation effect, but you can hear it all the way across the room. It's just fun. All right. Does anybody have any questions about that problem? Or tricks, things that you ran into? Yeah.
So I thought that P1 would be our normal atmospheric pressure, and P2 would be what we were solving for. So I ended up getting an increase in pressure.
This, yeah, that's like if you're blowing into it like this, which I'm not going to do because it's going to get water on me, then that's what would be going on, but we're not. So I'm blowing like this. The atmospheric pressure is inside the chamber the whole time. The flowing air has the lower pressure. And if you think about air as a random collection of molecules with a random collection of velocities, the one that's moving is going to be the one that has the effectively lower velocity because it's moving, the particles are moving in one direction relative to isotropic. So normally particles are moving in all directions. But when it starts to move, then they're preferentially moving in that direction, which reduces relatively how much that way is going. So you can also use this technique to decrease the air pressure in this bottle just by blowing across the top of it. It's not a great pump, but if you need to drop the pressure a little bit, it's effective. It's also how a carburetor works, for what that's worth. But I don't think anybody has a carburetor in their car anymore. Yeah.
Not the main car, but
in your main car?
yeah.
But in your weekend car?
Well, my dad's, but I've
Okay.
worked on it. So.
What is it?
77 Corvette.
Oh, all right.
Yeah.
Those are neat cars. Yeah.
Does the amount of fluid inside the bottle change like the pressure difference by a good amount?
It's not going to change the pressure difference. The pressure difference is primarily coming from how fast I'm blowing. What the liquid level does is it changes the boundary condition, so it changes how long the wave is. So it'll just change. It'll just change the volume. Not necessarily in intuitive directions. If you take a 3-liter bottle and you blow across the top of it and you squeeze the middle just a little bit, the volume goes down, but the pitch drops, and I don't understand why. But it has to do with the complex boundary condition of some kind of Bessel function, some kind of gnarly bottle-shaped Bessel function. So the pitch is different from the actual pressure. Okay. Okay, beginning with continuity and Navier-Stokes. I will do this one on the board in a second, but I'll roll the screen up before I do that so that I have the whole board real estate. So I'll come back to that one. Don't let me forget to come back to that one. Okay, plane parallel Couette flow. Does anybody have any trouble with this one? I think it seemed like everybody got it pretty well. So you basically, dV dt is 0 because we're in steady state. Vy is 0 because it's not flowing into the plate. And d by dx is 0 because otherwise you'd have a pileup of stuff. So you're left with just 0 because the whole time derivative of the velocity has to stay the same. It can't be accelerating along it because we made this infinite in length. And it can't be accelerating up and down because you run into the wall, and it can't be just accelerating in time because that violates us, how we set things up. So all of Navier-Stokes is reduced to just 0 equals mu times dv squared dy squared. That's the only term that survives. You've got vx in this direction, and it's got a derivative in y. And that's all that survives. Everything else goes away. And now we can integrate. We integrate once, and we get dv dy as a constant. We integrate again, and we get vy is
some constant times y plus b, and then we apply our boundary conditions. At y equals 0, vx has to be 0, so that goes away. And at y equals d, it has to be the velocity of the top plate. So we just plug these two pieces of knowledge into here, and we get that vx equals the velocity of the plate over d times y. So this is an intriguing result, because if I had started with Euler's equation, I would get nothing. If I start with Navier-Stokes, and the viscosity goes away, this viscosity cancels out. It does not matter what the viscosity is, it will get you this result. It will always get you this result, kind of regardless of the viscosity. And this is related to another result that we're going to touch on, but not really spend a lot of time on, but it'll come up. When we're talking about fluid turbulence, the dissipation of the fluid turbulence is an incredibly complicated topic that nobody understands. And I mean that pretty resoundingly. We have some models and some ideas, but fluid turbulence, a turbulent fluid will dissipate energy even if you turn the viscosity all the way down to 0. So even in the limit of 0 viscosity, turbulence will still dissipate energy. And this is similar, like even in the limit of 0 viscosity, we have to do the problem first and then take the viscosity to 0. But it doesn't matter what the viscosity is ultimately. What matters is the structures that are around the system. The same will be true for fluid turbulence. The structures that you build really matter. Here the structure is these two plates, and then whatever happens in the middle doesn't really matter what the viscosity is, you just need some viscosity to make it work. Okay, estimate the Reynolds numbers for these things. And here is an exercise in make up some numbers. So let's go through what I said. So air over an airplane wing flying from Detroit to Los Angeles. So the Reynolds number is L times V over the viscosity. So the wingspan of a plane is on the order of 5 meters. And a plane flies at about 250 meters a second. And the viscosity of the air is about 1.5 times 10 to the minus 5 meters squared per second. So that gives me a Reynolds number of like 10 to the 7. Did everybody get ish comparable numbers? You should get a pretty large number here, because the air coming off the back of an airplane wing, if you're not very careful, is very turbulent. So the same is true for owls. So have you ever seen videos? There's some really cool videos of owls flying.
Yeah.
There's this great video. They've set up a row of microphones, and then they put a mouse in a box or something, and they have a hawk fly down, and it goes, and it catches the mouse. And then the owl comes down, and it makes no sound at all. Why? Does anybody know what an owl does to make it fly without making any sound? Nobody watched that part of the video. That's cool. They have here's a schematic owl. Here's his feet. Here's his beak.
Like the way they move their
Yes.
wings is like kind of weird, almost like in a wavy way.
Yeah, they've got this ring of very small feathers right on the leading edge of their wing. And the very small feathers make little channels. So what does that do to the flow over the wing?
Makes it more streamlined.
Ultimately, what quantity does it reduce?
The Reynolds number.
The Reynolds number. Because now the length scale is little. So now you have all these little things, and the Reynolds number is a lot lower going over the wing than it is just even like relative to the thing just above the wing, because you have these little channels that drop the Reynolds number substantially, and so the owl can fly without any sound because its Reynolds number is really low. Because as you noticed in doing these problems, what is the dominant length scale is an important question, and I'm not going to be real picky about it because it's you waving your hands, but yeah.
Do scales on a fish also streamline, like help it streamline
Yeah.
the same way?
Yeah, shark scales have a groove in the top of them for the same reason. So that's why there are some swimming outfits that are not legal in competition because they're too streamlined. And they take a lot of their design from shark scales.
and fish scales because they have these grooves on them that drop the Reynolds number around the surface and make you go a lot faster. So you can have an illegal bathing suit because it's too fast in some competitions. But it all comes down to just this one simple combination of things, LV over nu. And nu you don't have any control over most of the time, so you have control over L and V. So, and V maybe you don't have control over either. So L is where you can change things. Water in a drinking straw. So think about what length scale is relevant. So for the velocity, I found that I could empty a 20 centimeter straw in a half a second. I went, not very scientific. So velocity is 40 centimeters a second. For L, I used the diameter of the straw. If you remember from talking about pipe flow, the length of the pipe kind of went away. The radius of the pipe is really what matters. So it's the width of the pipe that's the dominant scale here. And that's about a half a centimeter, unless you get one of those huge boba straws. I love that my favorite milkshake place in San Diego when I was a grad student started using those big ass boba straws, and it changed my mind about milkshakes entirely. Like I love a milkshake, but through a huge ass boba straw, it's like a magical thing. And then look what recently Lofty started doing that too. Do you guys know about Lofty Pursuits? Really? Oh man, you should go visit Lofty Pursuits. It's just north of the 10 in Market Square. It's an ice cream and toy shop, and they serve breakfast, and it's maybe my favorite store in town. They also make candy in this old Victorian style, which is the same way that my grandparents made candy when they had a candy shop in the 70s. It's a really Lofty Pursuits is the jam. But anyway, they have great milkshakes and big ass boba straws. So plugging all these in together, I get a Reynolds number of like 1,700. Did you guys get numbers that are comparable to that? Bigger, less?
Like 800.
Like 800? Yeah, like 1,000-ish. So that's a flow that's like starting to get turbulent, but isn't too crazy yet. Which is pretty similar. Like when you're sucking on a straw, you're not getting your face punched by the wind, but it is swirling around a lot. 3 ounces of whiskey neat that's been left untouched at the bar for 20 minutes as its owner stands outside smoking a cigarette, contemplating his failed marriage. This story went several different ways as I was writing the problem. And it got more elaborate and more hilarious every time, and I decided on this much neater solution. What is the Reynolds number of whiskey that's just sitting there? It is 0. It's just sitting there. The velocity is 0. Now, some of you talked about the micro motions, and we're not talking about the microfluid motions. The little motions are subgrid. That's all Brownian motion. That's all particle stuff. So that's not in Navier-Stokes. Yeah.
How would the ice affect the?
Well, okay. So it's not in. Ice would give you a temperature gradient, and that would cause motion, as we'll see in a minute. We're going to do convection in just a second. So the ice will cause the fluid to cool and will make little rolls, which is why there's no ice in this problem. So it's just a uniform temperature.
Like depending on the temperature, if there was evaporation of the liquid, in this case it's viscous, so it probably won't be. But if there was evaporation, then there would be a velocity flow through the.
Excellent point. So so it's alcohol that evaporates, so there's just going to be a flux of material. So there just has to be some low-grade velocity in that direction. So, kind of a dumb problem, but also kind of fun. 2 clouds of molecular hydrogens, each with a mass of 10 to the 5 solar masses and a number density of 100 particles per cubic centimeter and a temperature of 10 Kelvin. This is about how big real molecular clouds are in outer space. They collide with a relative velocity of 30 times their local speed of sound. And the viscosity you're going to find is nu is some particle speed times some particle length scale. So that's typically how you approximate a viscosity is a velocity times a length scale. Where the thermal speed is this, you can use this for the sound speed as well. The only difference is a 3 in here. And the mean free path is this. Now, when you're using the mean free path, I hope everybody got this hint. If you don't use the electron charge in
ESU, you get a very wrong answer because in CGS, this has a different form. There's some pi's and it's square root of an electron charge or some crap in MKS, so it's a different formula. So for the length, I just got the mass over the density and took the third root of that to get the size of the scale. And I got about 35 parsecs, which is 10 to the 20 centimeters. Did people do something similar for the length scalar? Más o menos?
I did the genes wavelength.
What's that?
I did the genes wavelength.
All right. The thermal velocity you get from here, which is about 2 times 10 to the 4 centimeters per second. Lambda, if you plug everything in that I gave you, you should get 10 to the 5 centimeters. This gives you a viscosity of 2 times 10 to the 9, which is very large. That's a large viscosity. But the length scale is 35 parsecs. That's how many parsecs are in a light year. There are 3 light years in a parsec, so this is 100 light years. This is a big object. So the Reynolds number is like 10 to the 16. So the Reynolds number in these is ridiculously large. Okay. Any questions on that? I will do the energy one.
Wait, sorry, what did you get for the mean free path?
10 to the 5 centimeters, which is a big mean free path. But
Oh yeah, no, there's something. I did something wildly wrong.
I got something embarrassing.
oh, what'd you get?
Oh, well, I mean, I got 10 to the negative 34.
10 to the negative 34 is a very small number.
But I got 10 to the 16 for Reynolds numbers.
Oh, really? Well, I'll look at what you did. Pardon me. Okay.
What was the difference?
So the total energy equation. So what we're, oh, actually, no, I'm good. So what we want to do is show that d by dt of rho e plus 1/2 rho v squared equals minus grad of 1/2 rho v squared v plus e plus p over rho. That's right, isn't it? You guys did this for homework. I'm just going off the memory.
Oh, there's a, yes.
Yeah, because the W is.
Yeah, because this is W.
You also need
There's 1/2
You need
each
it,
where you're-
sure.
You need the K delta T term.
Oh yeah, I'll skip the k delta t term for this because the k delta t term is, it just kind of hangs on, like nothing actually happens with that term. It just gets sucked into the v. So maybe I'll leave it.
Isn't the V squared and the V swap?
Yeah.
Yeah.
It's rho v
There's
times
1/2
half.
v squared on the inside.
That's good.
1/2 rho v squared.
So half is also inside.
Half is also on the inside. Thank you. I knew there was something wrong when I wrote it up. I was like, I did something wrong, but I can't remember what.
I think it's also dot, like divergence, instead of grad. Yeah.
Yeah. Okay, so if it's wrong, we'll see it.
No, yeah.
And it will be a mess when we're done. So okay, so we're gonna start with,
V to P.
um,
Undo that. No, it's all like.
oh, why am I doing it cold? I have it all written down. It's right here. If I just go off my notes, I'll get it right. Oh, actually, but I didn't. Yes, thank you, that is correct. And then we also have we can have a minus k grad t in there as well. Okay, so we're going to start with continuity, d rho dt equals minus div rho v. And I'm going to write them all with the time derivative on the left-hand side and all the space crap on the right-hand side. And then we have epsilon d by dt of, oops, sorry, rho d by dt of epsilon is equal to minus v div epsilon minus p div v minus k grad, minus div k grad t. So this term you can right away see where it's going to go, right? This term you don't have to do anything with. It's just going to go right there. It doesn't, nothing else happens. And then the last term, d by dt of v equals minus v dot grad v minus 1 over rho grad p. Okay, so the first thing we do, we start with the left-hand side and we blow this up. So the first thing we're going to do is blow up the left-hand side. And the second thing we're going to do is plug in all of these right-hand sides. And then the third thing we're going to do is look for all of the ways we can integrate by parts. Yeah.
I think the div k div t is plus. Is that plus?
Yeah.
Oh.
You take the other side.
Yes, that is what I have. Right, thank you. Okay, any other glitches? No? Okay, so let's start with this first term. So we're left with d by dt of epsilon dt rho plus rho dt epsilon plus, okay, what's the easiest way to do this?
V squared over 2 d3 rho.
Yeah, that's how I wrote it. So I can expand this in a couple of different ways, but I'm just going to do the obvious thing. So we've got 1/2 v squared d by dt of rho plus rho v d by dt of v. Right? So this is minus epsilon div rho v this one, rho de dt, is just this. I got a minus v dot grad e minus p div v plus k plus div k grad t. From this term, I get a 1/2 v squared minus div rho v. And from this term, I get a minus rho v v d, let's keep it as a grad v minus rho cancels out, and I'm left with v grad p, v dot grad p. Okay, was that everything? I think I have everything there. So now, what are we looking for? So this term is already of the form minus grad of minus k grad t. That's the same term, so we're sorted on that. So we're good here. Where's my color? So here and here, we're sorted. So now I have let's look at my epsilons. So I have an epsilon here, and then I have an epsilon here. And I have, let's look at my p's. My p's are here, and my p is here. Let's look at the p term first. So if I expand, let's simplify this a little bit. So this is equal to minus div 1/2 rho v squared v. That's his first term. Plus rho v epsilon plus vp minus k grad t. So all I've done is expand this out a little bit so that I can see what I'm looking for. So I need a row V, so I need a VP. So I've got a P div V and a V div P, and that in the square gets me div VP. Make sense? This term we're sorted. This term and this term give me my rho V epsilon. Ooh. I'm missing a row. There's a row here. I missed this row when I was writing it down. Yeah. So this term and this term combine to give me, I have minus grad rho V epsilon from this guy and this guy. And then from these terms, so this one is kind of harder to see, but it's basically the same thing. I've got a rho V and a V squared. I've got a rho V and a V squared, and I could just pack all these guys into here, and this gets undone by the same chain rule, and this one gives us that term there. Does that make sense? Does that seem to jive with what you guys basically did? Okay. Was that?
It's just that last step took me a while to figure out.
Yeah, it takes a minute of beating your head against it before it becomes clear. And even then, it's still a little tricky.
Something about product rule, even though you learn it in Calculus 1, I'll never grasp it. I'll probably won't grasp it for 15 years.
It's just so hard to see.
You'll get there sooner than that.
I don't know.
Yeah, it's one of the-
I promise.
It doesn't feel that way.
I understand that. But you'll get there because it's just two things. It's just breaking out two things and bringing them back together.
Yeah.
I think the biggest problem
You
is
just have to
like
beat your head against it long
Yeah.
enough.
simplify it down.
Okay.
Yeah.
Square.
Is that it?
Simplify it down.
Does anybody know where Nam Mashraki is?
It just doesn't have a class.
Okay, he doesn't. I haven't seen anything from him yet, so
Oh, okay.
that's going to be problematic. Not to talk crap about other students. I noticed that I haven't seen much from him. I will reach out to him. If you guys see him, tell him to reach out to me if he's having trouble. Okay. Oh, also, Hurricane Thursday, so probably no class. Watch it. Watch for it. I'll have class if the university's open. The university is generally pretty conservative. That's what they've been over the last few years. They're pretty ready to close school, so I'm really expecting that they'll close school midday tomorrow or Thursday morning, because I think landfall is supposed to be 8 a.m. Thursday. I don't know. Does anybody know how big this hurricane's supposed to be when it hits?
Cat 3.
Cat 3 or higher.
3?
Yeah, obviously three.
But since yesterday it moved eastwards, so before we were like right in the middle of it, like through the eye.
Yeah.
But since yesterday in the last 24 hours, it's basically moved more towards Jacksonville side, towards Live Oak. So like it's
Okay. A buddy of mine was like, "Oh yeah, I'm gonna go to St. Augustine."
no, it's not.
That's the wrong way.
Yeah, you gotta either go east or like slightly like sorry, west or northwest. But it's
Okay.
gonna go down from Cat 3 to a tropical storm like in a few hundred miles essentially.
I think it's gonna hit us at
So
Okay.
Or just like a.
So let us talk. Okay, so well, actually, this is super relevant because how does a hurricane work? So a hurricane works because of Coriolis force.
Let's predict how.
So you have the surface. So you're in a rotating system. So if I'm looking down from the top of here's Florida, here's Canada and Alaska, and California and Mexico, Baja. So the Earth is going. Which direction is it going? That way, right? So this is the North Pole. Here's Europe. So the Earth is rotating that way. So when I have the sun beating down on the surface of the ocean, or the Gulf, it's gonna make the water hot and evaporate. So the water then goes up and expands. What happens when you have if I have a rotating system and I expand outwards? I start rotating the other direction, right? Because you gotta conserve angular momentum. So you get bigger, have to conserve angular momentum, so you start rotating in the other direction. So the cyclones all spin in that direction because they're rotating in that direction because the air comes up and expands and is rotated by the Coriolis force. Why does the air rise? Because it's convectively unstable. Let us now do a lot of math about convective stability, which is exactly what I had planned for today. It kind of works out nicely that way. So many people really have absolutely no concept of just how much energy is in a hurricane. A lot of times I get questions about, does the MagLab actually help? What about, which is that's my favorite running joke, and I'll be honest with people, but I still love it.
I love to tell people that.
I know,
I love
right?
to spread that lie. It's so good.
It's pretty funny. But the energy density, I mean, think about the total energy in a hurricane. A hurricane is the size of the entire state, right? It's a huge object. The actual total energy is in the terajoules. Like, it's a really stupid amount of energy. A nuclear weapon is like 1/1,000,000th of a hurricane. So there's, or less. So the amount of energy in a hurricane, what'd you say?
Let's control hurricanes.
I know, right? Control hurricanes by spewing nuclear waste everywhere.
With the mask.
So no, nuclear weapons would not help because there's no way for you to actually stop that object because it's already spinning. And what are you going to do? Blow something up? That's going to expand. And what did we already cover that does? That starts to spin. So dumping nuclear weapons into a hurricane is only going to make it worse. So let's talk about convective stability. So I have a pot of water, or a star, or the atmosphere above the Gulf of Mexico, and it has some pressure and density. So at the bottom, I have some pressure and density, and as I go up, I have some P prime and rho prime. So I have some gradient in my pressure and density. And we sorted out some things about gradients of pressure and density in atmospheres when we did hydrostatics, and I think you'll do a little bit of that in the homework. It's pretty painless. It's pretty easy to get a gradient. If I've got gravity pointing this way, I'm going to get gradients in the other direction that counteract that gravity. The most obvious one is grad P has got to equal minus rho G. So the pressure gradient, that's the force you get, has got to equal the energy, the force you get from gravity. So that actually gets a little bit more complicated than that when you have a full round star and you're not looking at something small, but that's all right. So now I'm going to take a bubble. So here's my bubble. So let's call it a blob, because that's less to write. And it's going to start with some P and rho, and it's going to rise. We're going to push it up. Somehow it's going to go up. It's going to go up here to some P star, rho star. So now, when I'm up here, I'm going to have a different pressure and a different density. Now we're going to do this slowly enough. It's not so fast that we still have a pressure difference. So this bubble's coming up. It's going to just basically feel the pressure of the surrounding star all the way up. But the density is not going to necessarily equilibrate that fast. Because the density requires a momentum wave to change, but the pressure only requires a sound wave. So the sound wave goes really quick. Whereas changing the density requires actually material flowing into the blob. So we'll just do this. When is this going to float and go up? When does something float? Yeah, if it's less dense. So if rho star is less, let's get a statement for stability. If rho star is bigger than rho prime, then it's stable. And if rho star is less than rho prime, then it will convect. So we just need to sort out a criteria on the structure of the star such that we know which one of these is going to happen. So let's first talk about the background. So are these notes that I like? These notes have an error in them. I noticed I was going through my derivation and I was like, God, this doesn't work. Why does this not work? Oh, right, because I wrote that totally wrong. Pardon me, let me assemble my narrative flow. So the background pressure here, I can say that P prime is equal to P plus dP dz times delta z. So this is a height of, this is 0, and this is a height of delta z. So we're just linearizing the solution. And it doesn't matter what P is really doing. As long as I'm looking at a small enough region of my star, I can say this. So I might also have to say plus d squared z p, but that's small because it's a second order perturbation. So we just have a linear perturbation on the background solution. And we also know that rho prime is rho plus, is this how I want to do this? Yeah, d by dz of rho times delta z. We're going to come back to this in a second because d by dz of rho, well, let's have one. D rho dz is equal to dt d rho, no, sorry, d rho dt dt dz plus d rho dp dp dz. Okay, we'll come back to this in a second. So I've got a linearized statement for what my star is doing. And this we'll come back to. We're going to plug in the ideal gas law a couple of times. So I'm going to do that over there on the board. Let's talk about what the blob does real quick. So let's assume that the blob rises adiabatically. So it's rising faster than a sound wave can cross. It's rising slow compared to a sound wave, but fast compared to anything else. So this is relatively quick. But not supersonic, but nothing's supersonic unless it's exploding. So your pot on your stove is never supersonic. So we can treat this as basically adiabatically. So we can say that rho star is equal to rho times p prime over p to the gamma. So, oops, 1 over gamma. Because I know that p equals rho to the gamma for an adiabatic process. So I just set that statement true for both the initial and the final states. And I'm left with rho star equals rho times p prime over p. Okay, so we've got two things that we got to do a little work on. So we got to do a little work on this guy, and we got to do a little work on this guy. But what we're going to do is expand these out until we get to things that we can actually put our hands on.
or until we run out of things to actually say. And then we'll take the difference of these two terms and see if it's stable or not. And if it is stable, then we can look at the frequency that it'll oscillate at. And if it's not stable, we'll look at how fast it goes up. Okay, so starting with this guy here. So rho star equals rho times p prime over p to the 1 over gamma. I have an expression for p prime here. So we'll just plug this in. This is rho times 1 over p, p plus dp dz delta z to the 1 over gamma. And we could just expand this out and then do a Taylor series. So if I have 1 plus delta to the gamma, this is one of those Taylor series that you should just get kind of familiar with. So let's do it, and I might screw it up because I always screw this one up when I do it. I know what the answer is. The answer is 1 plus gamma delta. But let's prove that. So if we're going to say d by dx of d by d delta of this is just going to be a gamma comes down times 1 plus delta to the gamma minus 1. Then we evaluate that at delta equals 0 because we're expanding around delta equals 0. And we're just left with gamma. So you're left with your constant plus gamma times delta. Because this is dBz, so it's f at 0 plus x f prime at 0. Does that make sense? So f prime is gamma, x is delta, so that's what we're expanding it as. So did everybody follow that, or at least well enough? That was a little sloppy, but so I do a Taylor series and I expand this p. So this p goes here and here, and this gamma comes down, and we're left with rho times 1 plus 1 over p gamma d p dz times delta z. Now I have a statement that's linear in everything, because really one of the goals of doing any kind of physics theory is getting rid of the things that you can't solve by linearizing. And that is how basically all of it is done. Whenever you see a high energy talk, they're always talking about next to leading order terms and next to leading order terms. It's because to get the first theory, they linearize the crap out of everything. And then when you start putting those nonlinear terms back in, that's when you get these next terms. So linearizing is key. So this is one statement about P star. And let's look at P prime real quick. So we have d rho dt. So P equals rho T R over the molar mass, right? I can write this K over the particle mass as well. The only difference between R and K is Avogadro's number. The only difference between the molar mass and the particle mass is Avogadro's number. We'll use R because that's what the book does, and that's what chemists like to do. So I can say that, so we solve this for rho. So rho equals P over T times stuff. So dP, we need d rho dP is equal to 1 over R T times rho over P. And d rho dt is equal to minus 1 over T squared. Let's write this as, do a little bit of algebra and you get minus rho over T. So these two derivatives are just taking derivatives of the ideal gas law. And now we plug these back into here, into this equation, and I'm left with So this is rho star equals this. Rho prime is equal to rho times 1 plus d rho dt, dt dz. D rho dt is here, so we get a 1 from this row. We get a minus rho over t, d by dz of t, plus rho, oh no, I factored the rho out already, plus 1 over p dz dp. So this is actually relatively simple. So I'm just left with, so remember, I have rho prime, that's up here. It's just going to be rho plus d rho dz. We expand this guy with chain rule, but here, the blob, I can assume is adiabatic. But the background, I can't assume that this is adiabatic because I have other physics going on. I have a boundary condition at the bottom and a boundary condition at the top, and this may not be an adiabatic profile. It's going to be determined by what the boundary conditions are doing. So when I do the chain rule on rho for the background, I can't just say it's the sound speed times the pressure. I have to use both the temperature and the pressure variation. Does that make sense? Yay, no. So, okay, so a lot of times I need to say what is rho of z. And actually, a lot of times I need to talk about, say, d rho dz. If it's adiabatic, actually, let's say, well, when I said dp dz before, we just immediately replaced this as c squared d rho dz, where c squared is dp d rho. So this is an application of chain rule, but we've assumed that it's adiabatic. So density only depends on pressure. There's no temperature anymore because it's adiabatic, because I have this simple law. Here, when I use the chain rule, I only have one derivative. But if I don't have something simple like this, then I have to use all of the terms that density depends on. So density depends on now density, pressure, and temperature. So you need a pressure term and a temperature term when you do the whole chain rule. So now my chain rule just turns into 1 over t dt dz and 1 over p dp dz. So this is pretty nice. And simplifies things a lot. And then I've got up here, I only have a pressure term. So rho star only depends on pressure because we decided that's adiabatic, whereas the background depends on temperature and pressure because it's not adiabatic. So now we just take the difference. So what we need is we need rho star minus rho. Yeah?
So up until rho star, like that line that you just underlined, the units were checking out. But now, or I don't know, I just can't see for in your rho prime equation how your units, so does that matter?
Oh, I'm sorry, I need a delta z. Now we're good. So the delta z cancels out the z in the derivative, and the 1 over t cancels out the t in the derivative, and then so everything in here is dimensionless. Does that make sense? And then here, I've got a delta z that kills the delta z and a p that kills the p. So this is just a 1 over gamma. That's a good check. That's a good thing. So always be checking the units when you're going. That's a really great thing to be doing. So much easier to find out when you screwed up. You're looking at the units. There's this, in one of the code packages that I use for analyzing science data, they started making everything have units on it. And when they first started this, and it's the software package for analyzing simulation data. So I make the simulations and then I use the software package to analyze it. When they started enforcing units everywhere, I was like, Jesus Christ, this is going to suck. And I realized that there's a little bit of extra effort, but it winds up catching so many mistakes, so many little stupid bugs that I have caught just by having the code enforce units on me. So checking units is good. So we're just going to take the difference of these two things and rearrange. And so what we want is, here I'm just going to rewrite this. Rho minus rho star is bigger than 0 for stability and less than 0 for convection. So rho minus rho star is going to equal to
Rho prime.
rho star minus rho prime, thank you, is going to be equal to, how much of this algebra do I want to skip? So this is a 1 over p d p dz times a 1 over gamma. And here's a 1 over p d p dz. So when I take the difference, I'm just going to get a 1 minus 1 over gamma times dz of, I want to make this log p now. So d1 over v dv dx is equal to d log v dx. Everybody comfortable with that? Because the integral of 1 over x is log x. So I'm just going to replace this guy by a derivative of the log of the temperature and this guy by the derivative of the log of the pressure. That just makes it less stuff for me to type. I got a rho out front, and then I've got this term. This is my pressure terms. And then I got a plus 1 over, then it's just dz log t. So now, if we want stability, then this has to be bigger than 0. So now this is kind of gross. Let's simplify it a little bit. I can cancel out this rho because rho is positive definite. I know that rho is bigger than 0. If rho is ever actually 0, you have serious problems. Your fundamental processes fail. Your equations are no longer valid if rho is 0. So I can cancel the rho, and then I'm just left with 1 minus 1 over gamma times dz of log p has got to be bigger than dz of log t. This is the Schwarzschild convective stability statement. The pressure gradient has got to be bigger than the temperature gradient. And since the temperature gradient is negative, we put absolute values around all of these because both gradients are negative, but they have to work in that direction. I got 20 minutes done, that's cool. So I can simplify this. I can take this 1 minus 1 over gamma and put it up here in the exponent of the pressure and multiply through by a gamma, which gets me another gamma in the exponent. And then this can become, if I take the log of temperature and put it over here, then I'm left with d by dz of the log of the pressure to the 1 minus 1 over gamma. I got a plus. We're looking at this term here. Plus d by dz of log t. I can combine these two things because there's nothing in front of them anymore. So I combine the two derivatives and I combine the two logs, and I'm left with d by dz. Oops, goodbye. D by dz of the log of p to the 1 minus 1 over gamma times t has got to be, remember, this is still bigger than 0, bigger than 0. If I do a little bit of algebra, if I put a gamma, if I can multiply it through by gamma because that's positive definite, and then bring gamma upstairs, and then this turns into d by dz of the log of the entropy. That's got to be bigger than 0. So these two things are related. So the entropy gradient has to be positive if it's going to be stable. If the entropy gradient's negative, then you go up, you lose a bunch of entropy to the surrounding system, which is going to cause you to go up even further. So it's the same basic idea, but instead of shedding density, you're shedding entropy. So if the entropy gradient is not increasing, then you will be unstable. So if you go up and you lose entropy to the surrounding, then it'll keep going. Does that make sense?
So does unstable just mean like leave the atmosphere? Or?
No, so what it means is it will start to convect. And the next section, which I'm debating if I'm going to actually cover it because it's kind of long, and I don't know if it's exciting enough. You have some bottom where you have some heat source. Stuff is going to go up until it can't go up anymore. And so that can either be it hits the surface and then comes back down, or it could be that the temperature and pressure gradient have some complex behavior because, say, there's radiation. So the stellar structure is going to change things, is going to change how the actual behavior is and where this convection happens. But basically you just get cycles of stuff that rolls around around the star, just like if you look at like rice in a pot of water that's cooking, the rice gets carried up and around. The rice doesn't leave the pot, the water does, so the water, once it gets to the top, can evaporate. And that's where the stellar wind comes from. So we have the solar wind blowing off the wind, and that is the stuff coming up to the top and evaporating for whatever evaporation means when it's a fully ionized plasma. Okay. So positive entropy gradient, or these entropy gradients, or these gradients for the temperature and pressure for the star to be stable. Okay, so that's for it to be stable against convection. This isn't going to blow the whole star up or collapse it down to a point. Let's talk about what it takes to collapse the star to a point. When is the whole star stable or not stable? So let's talk about that. So now, this is all Chapter 7. So Chapter 7 reading is due allegedly tomorrow night. Go ahead and do it tomorrow. I'm not going to change the due date. Do it when you, like, if you wind up getting stuck in a hurricane and you're late, I don't care. Also, if you forgot to put in how long the homework took you, please go put it in the comments. Otherwise, it's a homework problem. It's 2 points. But that's, it's valuable for me to know how long things are taking people, especially on the homeworks, especially because I restructured the homeworks a little bit, and one of them's going to get really long. So I want to, know how long I can make it for what that's worth. Okay, so let's talk about the stability of an entire star. So this stuff is the first section in the reading. And now the readings are lagging the lectures, but that's fine. So let us talk about a star. And this is the last section in the chapter. So in the next chapter, Chapter 7 is about stability of systems. And it starts with just this kind of philosophical blah, which is interesting enough. But 7.1 doesn't really have anything in it. 7.2 is what I just did. So go through that. When you're reading, now you've seen it once. So now you should be able to follow the derivation a little bit better. So now when you're doing your readings on this stuff that you've already seen the derivation in class, you can ask more detailed questions about pieces that you don't understand. So please feel free to do that. Feel free to really look at the derivation. And I really think that the derivations are really they're really important because it's how you get from one place to another. And watching me do it is super easy because I'm good at it. But doing it yourself is where you really see where your understanding holes are. Because it's not super complicated, but there's a bunch of moving pieces, and it's complicated enough that I always have to look at how it works every year when I come back and do this. It's not like sound waves I could just do cold, but this I have to think about. Okay, so I have a star. And I have a point on the surface of the star. The star has a mass m, and I can say Navier-Stokes. We're just going to use Euler's equation. And Euler's equation right now is going to look like dv dt equals minus 1 over rho dp dr. I'm just going to simplify the gradient and just use the radial component. minus the gravitational force, which is gm over r squared. Now, you'll note that there's only one m here. This is the gravitational force per unit mass. So if you want the gravitational force like you normally are used to, that has two m's in it, gmm over r squared, right? But this is not a momentum. So this is a force per unit mass. This is a momentum change per unit mass. So the force that you feel on the top of the star is gm over r squared, and the force that you feel pushing you up is dpdr. So now we're going to linearize like crazy. So we're going to shrink or expand this star by an amount delta r. And so this whole chain of events is really just careful application of Taylor expansion. What is conserved? So I'm going to take my star and I'm just going to squeeze it a little bit, or expand it a little bit and see what happens. Now, if it's a stable star, it will oscillate. Oh, I forgot to talk about the Brooke-Messiah frequency. I forgot to talk about the frequency. Read the Brooke-Messiah frequency. Just because I forgot to talk about it doesn't mean it's not important. You can take this and get an oscillation frequency out of it. It's real easy. You'll see how when you do the reading. Here, we'll have a similar thing. We can get an oscillation frequency that the star will vibrate at, or if things aren't set up right, the star will collapse. So let's go see what either the frequency or the statement for collapse. So what can I say? So my background solution is R naught and yeah. So remember how we linearize things. So we're going to linearize things and then look at stability. We're not going to do the whole Fourier analysis because we don't need to. It's going to be more obvious than that. But we have a background solution at R naught, and we know that the star is stable at R naught with some mass m and some pressure gradient p naught, but I don't actually need that. Oh no, I do. It's got some background pressure p naught. So we're going to expand, and we're going to say that R equals R naught times 1 plus delta. Now, why am I writing it that way? It winds up being a lot easier to parameterize it with this 1 plus delta here. I could get the same answer if I called this R naught plus delta, but this 1 plus delta makes my life a little easier. So density is mass over R cubed, right? So density is rho naught times R naught cubed divided by R cubed. So this is equal to rho naught times 1 plus delta cubed over 1, or sorry, R naught over, let me do this down here. This is bad board management skills. R equals R naught 1 plus delta. Rho is going to equal rho naught times 1 minus 3 delta. One of my favorite Homer Simpson lines. He says, I got 3 kids and no money. Why can't I have no kids and 3 money? So 3 delta. Why is this? It's because density is equal to mass over radius cubed. So this is going to equal rho naught R naught divided by R naught over R, which is just going to be rho naught 1 plus delta to the minus 3. That makes sense?
Wait, that says rho equals rho naught of 1 minus.
So rho is m mass over r cubed. Mass is rho naught r naught cubed over r cubed.
Right,
That make sense?
yeah.
And so I'm going to plug in this r into there.
What is, sorry, I just don't know what the 1 minus 3 delta, beta, 3 delta?
3 delta, yeah.
Okay.
Yeah. We'll get there in a second.
Okay.
So I'll get here.
Okay.
How do I get here? So rho is m over r cubed. So that's going to be, the mass is going to be rho naught r naught cubed. That's the total mass, and that doesn't change. Divided by the actual radius, which is r cubed. Everything's going to cancel out, so I'm just left, or the r naught's going to cancel out, and so I'm just left with rho naught 1 plus delta to the minus 3. This is nonlinear. We don't like nonlinear things. How do I linearize this? And what do I get?
Oh, okay. I see.
You get 1 minus 3, don't you? I'm not going to lie to you. This one, when I went through it, I was like, what the? Oh, okay.
Random 3, yeah.
Where did this 3 come from? Oh, I see. And the book is like, it is easy to show that. And it is. Like, it is easy to show. Like, it's really not that hard. You just have to write it down and make all the same assumptions that the author did, which sometimes that's straightforward and sometimes it isn't. So rho is going to be rho naught 1 minus 3 delta. This minus 3 comes from the minus 3 here, so this minus 3 here. And then pressure is going to be P naught times 1 minus 3 delta gamma. Why do I get a gamma there? For the same reason. It's another Taylor series. So I'm going to write pressure equals rho to the gamma. And I know rho, and it's going to be this to the gamma, and I'm going to do another expansion, and another gamma comes down. So I'm just left with P is P naught 1 minus 3 gamma delta. That makes sense? Oh, man. I feel like I time warped by 15 minutes. I swear it was, I had 20 minutes just like 4 seconds ago. Now I'm running out of time. Anyway, so now we just plug these back into my constituent equation, and we're left with dv dt equals minus 1 over rho naught times 1 minus 3 delta times dp naught times 1 minus 3 delta gamma dr naught times 1 plus delta. So I'm just taking this and I'm just plugging in what I know. Minus gm over r squared, but this is r naught squared 1 plus delta squared, which is just minus gm over r naught squared 1 minus 2 delta. Running out of board space. I will do this again with better board space. Actually, I'm running low on time. I'm going to skip a little bit of algebra. So you do a little bit of algebra from this point. And so you have this equation that you write down, which is just taking this, plugging in your linearized stuff, and then you take this, your background solution, and you'll see that this is in what you wrote down, and you take that out. And you're left with dv dr equals minus gm over r naught cubed times 3 delta times gamma minus 4/3. And actually here we stop. So now I could do some Fourier analysis on this, because I have a differential equation. So I could do some Fourier analysis on this and look at what modes are stable or not stable. Or I could just look at the answer. So the pressure term goes away. So all I'm left with is the deviation and the gravity term. And I have this gamma minus 4/3. And so this is what tells me if the star is going to collapse or not. Because G is positive definite, M is positive definite, R naught is positive definite. This term is negative definite, so that is a decelerating force. This term, if gamma is bigger than 4/3, then you have a decelerating term. But if gamma is less than 4/3, and it's a very squishy gas, then you will have a positive sign on the right-hand side. So dVdr will enhance delta, so you have runaway collapse if the right-hand side is positive. You don't if the right-hand side is negative. You have something that will oscillate. And that's all I got for today. This derivation is intriguing and cute. It's mostly useful because it's all of these instances of Taylor expansions that you can use. Okay, nominally there's a reading due tomorrow. You should just do it. So if you wind up not getting to it because you had to evacuate, that's totally all right. But then you're going to be evacuated and have nothing to do, which is a great time to do some reading. All right, see you guys soon. Stay safe.